How long can a memory last? Not the fleeting recollections of a human mind, but the echoes of creation itself, etched into the fabric of space-time. We believe the universe has laws immutable and eternal that govern the birth, life, and ultimate demise of everything within it, especially the stars. We look out into the cosmic dark and see not just points of light, but ghosts. We are peering into the past, receiving messages from suns that may have vanished from existence long before their light completed its journey to your eye. This is the nature of astronomy, a conversation with the long dead. But what if one of those ghosts began to speak back? What if a star whose life should have ended in a blaze of glory and whose corpse should have cooled into eternal silence refused to accept its fate? Out there, shrouded in the ethereal veils of a stellar graveyard, an object that by all our calculations died 10,000 years ago is broadcasting a steady rhythmic pulse. A heartbeat from a corpse. It is a profound and unsettling enigma, a signal that rips apart our neat theories of stellar evolution and forces us to question the very finality of death in the cosmos. This is the story of an impossible object, a phantom lighthouse in the celestial ocean. It is the chilling, captivating tale of a zombie neutron star. To understand the impossible, we must first journey back to the moment of its violent birth, an act of cosmic alchemy so extreme it beggars all imagination. Our story begins not with a whisper, but with the most powerful explosion the universe can unleash, a supernova. Imagine a star, a true behemoth, at least 10 times more massive than our own sun, nearing the end of its magnificent reign. For millions of years it has been a titanic nuclear furnace, a self-sustaining fusion engine converting hydrogen into helium, then helium into carbon, and onward, forging heavier and heavier elements in its core. This process, this delicate balance between the outward pressure of nuclear fire and the inward crush of its own colossal gravity, is the very definition of a star's life. It is a war waged on a scale we can barely comprehend, a gravitational siege held at bay by thermonuclear fury. But this war cannot last forever. The star's fuel supply is finite. As it desperately fuses lighter elements into heavier ones, it climbs the periodic table, a frantic scramble against its own inevitable collapse. Carbon, neon, oxygen, silicon, each stage of burning is hotter, faster and shorter lived than the last. The final stage, the fusion of silicon into iron, is the star's death sentence. Iron is the ultimate ash. Fusing it into heavier elements doesn't release energy, it consumes it. The fire in the heart of the giant sputters and dies. In less than a second, the equilibrium that sustained the star for eons is shattered. The outward pressure vanishes. What happens next is not a slow decline, but a cataclysmic failure of physics. Gravity, the patient, relentless force that has shaped the star its entire life, finally wins its long war. The star's iron core, a sphere larger than our Earth, but now bereft of its energy, succumbs to the crushing weight of the stellar layers above it. It implodes. The core collapses in on itself at almost a quarter of the speed of light, a cosmic freefall of unimaginable violence. Temperatures skyrocket to 100 billion degrees, a heat so intense it tears the newly forged iron atoms apart. The core shrinks from the size of a planet to the size of a city in a fraction of a heartbeat. The compression becomes so extreme that the very structure of matter breaks down. Protons and electrons, the fundamental building blocks of atoms, are forced together in a quantum mechanical shotgun wedding, crushed into a new form of matter neutrons. The entire core becomes a single gigantic atomic nucleus. This super-dense ball of a neutron matter, this newborn stellar remnant, finally pushes back. The collapse halts with the force of hitting a wall made of space-time itself. The infalling outer layers of the star, still oblivious and plummeting inward, slam into this unyielding neutron core. The result is the most powerful shockwave in the universe. It rebounds outward, tearing through the star from the inside out, a celestial pressure wave of pure destruction. This shockwave, supercharged by a flood of ghostly particles called neutrinos, reignites the remaining fuel in the star's outer layers in a final, definitive blast. The star detonates. For a few brilliant weeks, this single dying star can outshine its entire home galaxy, radiating more energy than our sun will in its entire 10 billion year lifetime. It is a spectacle of both death and creation. The explosion seeds the surrounding space with the heavy elements forged in the star's heart, the carbon in your cells, the oxygen. You breathe the iron in your blood. All of it was born in a crucible like this. The supernova's fading light leaves behind a breathtakingly beautiful expanding cloud of gas and dust. A nebula, a celestial tombstone marking the grave of a giant. But at the heart of this ghostly memorial, something extraordinary remains. The core, the crushed, compacted remnant that triggered the entire event. We call it a neutron star, and it is without exaggeration the most extreme and alien object that our laws of physics permit. It is a paradox made real, a cosmic monster hiding in the dark. The sheer density of this object defies all earthly analogy. Imagine taking Mount Everest, grinding it to dust and compressing it until it fits into the palm of your hand. Now imagine taking every car, every building, every mountain, every human being on the entire planet Earth and crushing it all down to the size of a sugar cube. Even that fails to capture the reality. A single teaspoon of neutron star material would weigh more than all of humanity combined billions of tons. It is matter stripped of its identity, where the space inside atoms has been completely annihilated by gravity. This density warps the universe around it. Gravity on the surface of a neutron star is 200 billion times stronger than on Earth. If you could somehow stand on its surface, you would be instantly flattened into a monatomic smear, your very atoms spread across its crust like a thin layer of paint. Light itself struggles to escape its pull, its path bent and distorted in a dizzying display of Einstein's relativity. The star acts as a gravitational lens, warping the view of the cosmos behind it. It's a gravitational gyroscope spinning with incredible speed. Thanks to the conservation of angular momentum, the same principle that makes a spinning ice skater speed up when they pull their arms in the slow rotation of the original star is amplified immensely as its core collapses. A newborn neutron star can spin hundreds of times every second faster than the blades of a kitchen blender. Its surface is a blur, moving at a significant fraction of the speed of light. And then there is its magnetic field. This too is amplified by the collapse, squeezed and concentrated to a level of intensity that is almost supernatural. A typical refrigerator magnet has a field strength of about 50 Gauss. A powerful MRI machine might reach 30,000 Gauss. The magnetic field of a neutron star can be a quadrillion times stronger than Earth's, a trillion times stronger than even the most powerful magnets we can build. It is a force so potent it could rip the iron from your blood cells from 1,000 miles away. It is a field so extreme it can distort the quantum vacuum, twisting the very fabric of empty space around it. This combination, the rapid spin and the ferocious magnetic field, sets the stage for the neutron star's second act. It transforms the silent, dense core into one of the most reliable clocks in the universe, a pulsar. A pulsar isn't a different kind of star, it's a neutron star that we can see. Its magnetic poles, much like Earth's, are typically not aligned with its rotational axis. As the star spins, its magnetic field whips through, space trapping and accelerating any stray charged particles. These particles are funneled towards the magnetic poles and shot outwards in two tight, brilliant beams of electromagnetic radiation, radio waves, X-rays, even visible light. The neutron star becomes a cosmic lighthouse. As it rotates, these beams sweep across the cosmos. If one of those beams happens to slice across our line of sight here on Earth, our radio telescopes register a brief sharp pulse. The star spins, the beam sweeps past again, and we detect another pulse. The effect is a rhythmic beat, a celestial metronome ticking away with a precision that can rival our best atomic clocks. For decades we have used these pulses to test the laws of physics, to map our galaxy, and to hunt for the subtle ripples of gravitational waves. Pulsars are our cosmic laboratories, their predictable behaviour, a testament to the order underlying the universe. But this cosmic lighthouse cannot shine forever. The process is fundamentally unsustainable. Broadcasting those powerful beams of energy into the void comes at a cost. The energy has to come from somewhere, and it is drained directly from the star's rotation. With every single pulse, every sweep of its celestial searchlight, the neutron star sacrifices a tiny, infinitesimal fraction of its rotational energy. It is a spinning top that is slowly but inexorably winding down. The ticking of the cosmic clock grows ever so slightly slower over the millennia. We can measure this spin down with incredible accuracy. It is a predictable, well-understood process governed by the laws of electromagnetism. A young, fast-spinning pulsar loses energy rapidly, its pulse period lengthening measurably over just a few years. An older one spins down more gracefully, its decline more stately and serene. Ultimately, this decline leads to a definitive end. There is a theoretical boundary in astrophysics known as the pulsar death line. It is not a physical place, but a threshold of existence. As a pulsar ages and its rotation slows and its magnetic field weakens, it eventually reaches a point where the physics that generates its beams simply fails. The electrical potential is no longer strong enough to accelerate particles effectively. The lighthouse lamp sputters, the beams flicker and die, the star crosses the death line and the pulsing stops. Forever, it falls silent. It does not explode or fade away, it simply ceases to be a pulsar. It becomes what it was always destined to be: a cold, dark, spinning sphere of degenerate matter, a dead cinder adrift in the eternal night of the galaxy, detectable only by its immense gravity. Its story, for all intents and purposes, is over. This is the accepted, verified life cycle. A star is born in fire, it dies in a cataclysm, its corpse spins as a beacon for a time, and then it embraces the final, inevitable silence. And it is here, at the very edge of this celestial graveyard, that we find our ghost. In a quiet corner of our Milky Way galaxy, nestled within the fading gossamer remnants of a supernova that lit up our prehistoric skies, lies a pulsar catalogued as PSR J-1-8. By measuring its current spin rate, and the rate at which that spin is slowing down, we can rewind the cosmic clock. Our models, the very same ones that have accurately predicted the behaviour of thousands of other pulsars, are unequivocal. This neutron star is ancient. Its spin has decayed to a leisurely rate of once every 1.2 seconds, a snail's pace for such an object. Its magnetic field has weakened over the eons. Based on every law of physics we hold dear, this star should have crossed the pulsar death line a very, very long time ago. Our calculations tell us that its lighthouse beams should have extinguished around the same time human civilization was taking its first tentative steps, when our ancestors were learning to cultivate the land and build the first settlements. It should have gone quiet 10,000 years ago. It should be a dead object, a silent tombstone for the massive star that preceded it, and yet it is not. Against all logic, in defiance of all our theories, it continues to broadcast its signal. Pulse, pulse, pulse. A steady, unwavering rhythm reaching us across the light years, a ghostly heartbeat, from an object that has no right to have one. It is the weakest pulsar ever detected, a faint whisper from the abyss, but it is undeniably there. It is a zombie, an undead star that refuses to accept the silence of the grave. This isn't just a minor astronomical curiosity, it is a profound cosmological crisis. It's as if we found a burning candle that had been sealed in an airless tomb for a century, its flame still flickering brightly. The observation makes no sense. The energy source that should have been extinguished millennia ago is somehow still active. What power source is animating this cosmic corpse? How can a dead star continue to send messages from beyond its own demise? Is there some unknown mechanism, some loophole in the laws of stellar death that we have never before witnessed? Could it be drawing energy from the very fabric of space-time itself, or siphoning matter from an unseen companion? Or does it hint at something far more revolutionary, a new kind of physics operating in the ultra-dense, high-energy environment of a neutron star's interior, a process that can resurrect a pulsar from its own ashes? The existence of this single object challenges the foundations of our understanding of compact stars and high-energy astrophysics. It forces us to confront the possibility that our story of stellar life and death is incomplete, that there are chapters we have not yet even dreamed of. To solve this mystery, we must become cosmic detectives, piecing together clues from a faint signal that has travelled for centuries to reach us. We must venture into the heart of a dead star and ask the most fundamental question of all: what does it truly mean for something in the universe to die? In the grand theatre of the cosmos, there are no quiet endings for the greatest of stars. There is only fire transfiguration and a legacy written in the most extreme physics imaginable. For stars-born titans many times more massive than our own, sun life is a furious blaze. For millions of years, they are celestial forges crushing hydrogen into helium, then helium into carbon-oxygen, and all the heavier elements that seed the universe, the very elements that make up the ground beneath your feet, the air you breathe and you yourself. But this act of creation comes at a terrible price. Deep within the heart of such a star, a countdown has been running since its birth. The furnace cannot burn forever. Eventually the core produces iron, the ultimate cosmic ash. Iron is a dead end. To fuse it requires more energy than it releases. The fire that held a star up against its own colossal gravity for eons is suddenly catastrophically extinguished. In that profound silence, gravity, the universe's most patient and relentless force, wins. What happens next is not a slow collapse, but a cataclysmic failure of physics. The star's core, a sphere of iron larger than the Earth, begins to fall inward on itself. It is an implosion of unimaginable violence reaching speeds of over a quarter of the speed of light. An entire world's worth of matter is crushed downwards in less than a second. The temperature skyrockets to 100 billion degrees, a heat unseen since the Big Bang. The very atoms themselves are annihilated. Protons and electrons, the fundamental building blocks of matter, are violently slammed together. Their identities are erased, their charges cancelled out, forced to merge into a new exotic state, a sea of pure neutrons packed together with a density that defies all earthly comparison. The core, once thousands of miles across, is now a sphere barely the size of a city. It has become so dense it can be compressed no further. It becomes incompressible, a solid wall of nuclear matter. The rest of the star, still collapsing inwards, smashes into this newly formed, unyielding object. The result is the most powerful rebound in nature. A shockwave of titanic proportions erupts from the core, tearing outwards through the star's falling layers. It is a wave of pure energy and liberated neutrinos, an unstoppable tsunami of force. This shockwave is the supernova. For a few brilliant weeks, this single dying star will outshine its entire home galaxy of billions of stars. It is the universe's grandest funeral pyre, a final defiant scream of light that can be seen across millions of light years. It scatters the elements forged in its heart across the void, enriching the cosmos, providing the raw materials for new stars, new planets, and perhaps new life. But our story does not end in this beautiful fading cloud of stellar dust. Our focus is on what was left behind, hidden in the heart of the expanding wreckage. The corpse, the ghost of the star that was. This is the birth of a neutron star. What you're looking at is one of the most extreme objects we have ever discovered. It is the remnant of that violent collapse, a perfectly spherical ball of neutrons, perhaps only 12 miles in diameter, yet it contains more mass than our entire sun. Try to imagine that. Take a star 1.5 times the mass of our own, a body so large you could fit over 1 million Earths inside it, and crush it down until it would fit comfortably within the boundaries of a major city. The density is so absurd, so utterly alien to our experience that analogies begin to fail us. We say that a single teaspoon of neutron star material would weigh billions of tons, more than all the cars, buildings and people on Earth combined, more than Mount Everest. But even this fails to capture the reality. You could not hold a teaspoon of it. Its gravity is 200 billion times stronger than Earth's. It would not sit on the spoon. It would tear through you through the entire planet as if you were nothing more than smoke pulled down to the Earth's core in an instant. This is not merely dense matter, it is the very edge of reality itself. It is matter on the verge of collapsing entirely, one step away from becoming a black hole, a gravitational singularity from which not even light can escape. On the surface of a neutron star, the laws of physics are twisted into a nightmare landscape. The immense gravity has smoothed its surface to an almost impossible perfection. Any mountains or surface features relics of its chaotic birth have been flattened to a height of mere millimeters. The escape velocity from this tiny world is more than half the speed of light. If you could somehow stand upon its crystalline iron crust, that colossal gravity would stretch and compress your body at the atomic level, pasting you across its surface in a layer of subatomic particles 1 atom thick. It is an object so far removed from our intuition it forces us to rethink the very nature of existence. But this stellar corpse is not inert. It is a dynamic, violent and powerful engine. The collapse that created it bequeathed 2 critical properties from its parent star, rotation and magnetism, now amplified to godlike proportions. Think of an ice skater pulling in her arms to spin faster. This is a law known as the conservation of angular momentum. The parent star may have rotated slowly, perhaps once every few weeks, but as all of its mass collapsed from a volume of millions of miles down to just a dozen, the rotational speed was conserved and magnified to a frenzied, blistering pace. The newborn neutron star can spin hundreds of times every single second, an object more massive than the Sun, rotating faster than the blades of a kitchen blender. It is a gravitational gyroscope of almost perfect stability, a celestial spinning top of terrifying power. And then there is the magnetic field. The original star's magnetic field, already powerful, was woven into its plasma. As the core collapsed, this field was dragged inward, squeezed and concentrated into an infinitesimally small space. The result is the most powerful magnetic field in the known universe. Not thousands, not millions, but quadrillions of times stronger than the magnetic field of our Earth. This is a force so powerful it can distort the shape of atoms themselves. It would wipe every credit card and hard drive on our planet from a distance of 100,000 miles. This is not merely a cosmic magnet, it is a dynamo of creation and destruction. This combination of rapid rotation and an ultra-powerful magnetic field transforms the neutron star. It turns the stellar corpse into something else entirely. It becomes a pulsar. Here is the great revelation, the solution to a puzzle that baffled astronomers for years. Crucially, the magnetic poles of the neutron star are not aligned with its rotational axis. Imagine the Earth. Its geographic north pole, the point around which it spins, is in a different location than its magnetic north pole, the point your compass needle seeks. On a neutron star, this misalignment has spectacular consequences. The intense magnetic field tears charged particles, electrons and positrons from the star's surface. It then funnels them along its magnetic field lines, accelerating them to nearly the speed of light. As these particles spiral outwards, they unleash a torrent of electromagnetic radiation, primarily in the form of intensely focused radio waves. 2 beams of energy, like the beams of a celestial blowtorch, fire out from the neutron star's magnetic poles, blazing across the cosmos. Now add the ferocious spin. The neutron star is spinning, and these magnetic poles, these cosmic blowtorches, are spinning with it. The effect is that of a lighthouse. The star itself is not flashing on and off. It emits a constant, steady beam of energy. But because it is rotating, these beams sweep across the void like a searchlight. And if you on a distant planet like Earth happen to be in the path of one of those sweeping beams, you will see a pulse of energy flash across your radio telescopes. The beam passes and there is silence. Then as the star completes its rotation, the beam sweeps past you again. Another pulse. Spinning hundreds of times a second, it produces a staccato rhythm of pulses with a regularity so precise, so unfathomably accurate that when they were first discovered in 1967 by Jocelyn Bell Burnell, the signal was playfully labelled LGM1 for Little Green Men. No natural phenomenon was thought to be capable of such perfect timing. These pulsars became some of the most reliable clocks in the entire universe, their rhythm a testament to the pure physics of a spinning celestial body. For thousands of years, this cosmic lighthouse will sweep its beam across space. Its pulse is a declaration that even in death, the heart of a great star can still burn with a furious energy. It is a metronome counting out the seconds against the vast silent backdrop of deep space. But even this spectacular afterlife cannot last forever. The pulsar is not a perpetual motion machine. It is slowly, inexorably dying. The very act of broadcasting those powerful beams into space comes at a cost. The energy for that radiation is being drawn directly from the star's rotation. With every pulse, with every particle flung out into the cosmos, the neutron star radiates away a tiny fraction of its spin. It is a form of cosmic friction, an electromagnetic braking that works on a timescale of millennia. The frenetic spin that began at its birth, hundreds of revolutions per second, gradually begins to slow. Over tens of thousands or perhaps millions of years, the process continues. The interval between each pulse grows longer by infinitesimal amounts, a few nanoseconds every year, but the trend is relentless and irreversible. The cosmic metronome is winding down. At the same time, the colossal magnetic field that powers the entire system also begins to decay. Its own internal currents and stresses cause it to weaken over vast stretches of time. The celestial dynamo loses its charge. The beams of radiation grow dimmer, their energy fading as their power source dwindles. Eventually, the star approaches a theoretical boundary known to astronomers as the pulsar deathline. It is a threshold of both spin and magnetic strength. Once a pulsar's rotation slows too much and its magnetic field becomes too weak, the engine in its heart can no longer generate the powerful radio emissions. The mechanism that accelerates particles and creates the beams simply sputters and fails. The lighthouse goes out. The pulse, that rhythmic signal that once beat with perfect precision across the galaxy, ceases. It stops forever. What remains is what the neutron star was always destined to become, a cold, dark, silent sphere of super-dense matter. Still massive, still possessing immense gravity, but now invisible to our radio telescopes, no longer broadcasting its existence to the universe. It becomes a true cosmic ghost, wandering the stellar graveyard of the Milky Way. Its brief, spectacular second life as a pulsar now just a fading memory. This is the accepted, understood and observed life cycle. A violent birth in fire, a brilliant but temporary existence as a pulsating beacon, followed by a long, slow fade into a quiet, eternal darkness. This is the fate prescribed by our laws of physics for every neutron star. A definitive and final end to its story, or so we had every reason to believe. And so our hunt brings us to the very edge of that cosmic graveyard, the silent, sprawling expanse where the universe's most extreme objects are meant to rest for eternity. We had been taught to expect nothing from this realm but the quiet hum of the background cosmos. It is a place defined by an absence of evidence, a domain where the furious engines of dead suns have finally blessedly fallen still. We were searching for ghosts, for the faint gravitational tombstones of stars long vanished. We were not under any circumstances expecting one of them to whisper back. The search began not with a lens but with a net, a digital net cast across an impossibly vast ocean of sky, woven from the most sophisticated algorithms humanity could devise. In the rust-red heart of the Australian outback, an army of antennas stood listening, a metallic forest of thousands of individual receivers tuned to the faintest murmurs of the ancient cosmos. This was the Murchison Wide Field Array, our ear pressed firmly to the celestial grave. Its job was not to look, but to listen with an almost unimaginable sensitivity, recording the static of the universe, the chaotic symphony of a billion distant sources all broadcasting at once. Buried within that cacophony, our science demanded there had to be a pattern. The sheer volume of information was staggering, a deluge of data so immense that no human team could ever hope to sift through it. Every second, the array poured terabytes of raw cosmic noise into the belly of a supercomputer, a relentless flood of information describing a patch of sky larger than any single telescope could ever hope to image. Our quarry, if it even existed, would not be a shout. It would be a single rhythmic breath lost in a hurricane of sound. So we taught our machines what to look for: a pulse, a repeating signal, the telltale signature of a spinning neutron star. We programmed them to recognize the frantic machine gun-like drumming of a young pulsar, the steady beat of a middle-aged one, and even the slower, more languid rhythm of an object nearing the end of its life. But we also gave them a new directive, a command born of a tantalizing, almost heretical hypothesis. We told them to listen for a heartbeat that was pathologically slow, a rhythm so lethargic, so drawn out that by all conventional logic it should not exist. We were asking them to find a signal that our own theories had dismissed as a physical impossibility, a ghost in the cosmic machine. For months, the digital sentinels watched and listened, filtering, sorting and discarding trillions of meaningless signals. They analysed interference from orbiting satellites, discounted the random noise of distant galaxies, and ignored the familiar signatures of known pulsars. It was a process of elimination on a cosmic scale, a search for a single anomalous note, in a universe full of sound. And then one Tuesday afternoon, buried deep within a data block labelled with an unremarkable string of numbers and letters, the algorithm flinched. It flagged a signal. It was not a strong signal. In fact, it was breathtakingly faint, barely distinguishable from the background hiss of the cosmos. And it was not fast. It was the opposite of fast. The system registered a single coherent pulse. Then for an agonizingly long time, nothing. The software waited, its internal clock ticking away, cross-referencing, checking for errors, preparing to dismiss the event as a momentary glitch in the hardware, a phantom echo in the system. But then, just as it was about to discard the data point, it happened again. Another pulse identical in shape and strength to the first arrived from the exact same point in the sky. The interval between them was so long that at first the astronomers who saw the notification believed it had to be a mistake. Conventional pulsars spin hundreds of times per second. Even the slower ones complete a rotation every few seconds. This anomaly, was pulsing with a period that stretched for nearly an entire hour. It was less a heartbeat and more a single drawn-out spectral sigh. The initial reaction was not excitement, but deep, profound skepticism. It had to be terrestrial interference. A faulty microwave oven at the research station, a bizarre reflection from a high-altitude aircraft, or some unknown atmospheric phenomenon. The team ran every diagnostic imaginable, trying to kill their own discovery before it could even be born. They checked the timing systems, recalibrated the antennas, and scoured logs for any possible source of contamination. Yet every test came back clean. The signal, faint and sluggish as it was undeniably real. And it was coming from a point far beyond our solar system, beyond our local stellar neighbourhood, from the cold, dark depths of interstellar space. The alert went out across the globe, an astronomical telegram fired off across secure networks, carrying a set of celestial coordinates and a simple, urgent plea: look here. This was no longer a task for a single instrument. To confront a mystery of this magnitude required a global conspiracy of scientists, a planetary effort to bring our most powerful eyes and ears to bear on one insignificant-looking patch of sky. From the high arid deserts of Chile, the European Southern Observatory's very large telescope swiveled its colossal mirrors, hunting for the faintest flicker of visible light from the source, hoping to find the stellar cinder that was producing this bizarre radio call. It saw nothing, just the cold, unforgiving blackness of the void. In orbit, high above the distorting veil of Earth's atmosphere, the Chandra X-ray Observatory turned its sensitive gaze toward the coordinates. Young, energetic neutron stars are supposed to glow in X-rays, their superheated polar caps blazing with radiation. Chandra stared for days, accumulating every precious photon it could. It too saw nothing, a complete and utter absence of high-energy radiation. The emptiness was in itself a terrifyingly important clue. The lack of an optical or X-ray counterpart meant this object was not young. It was not hot. It was old, cold, and seemingly invisible to all but the most sensitive radio antennas on the planet. Other radio telescopes joined the chorus, the Parkes Observatory in Australia. A venerable dish responsible for discovering hundreds of pulsars confirmed the signal's existence, its sheer size allowing for a more precise measurement of the pulse profile. In South Africa, the Meerkat Array, a precursor to the Square Kilometre Array, dedicated a portion of its immense power using its network of dishes to triangulate the object's position with pinpoint accuracy. Each new observation added another layer of impossibility to the puzzle. The signal was not drifting, it was not varying. It was uncannily, unnaturally stable, a pure, unwavering tone echoing across thousands of light years. It was the ghost of a rhythm, a celestial metronome ticking with a patience that defied belief. Every 57 minutes, like clockwork, it would send its feeble pulse across the cosmos, a single lonely lighthouse beam sweeping through the darkness. With its position now locked, the true nature of the confrontation could begin. Astronomers could finally bring the full weight of physics to bear on this enigma. The first step was to measure not just the period of the pulse, but the rate at which that period was changing. This is the crucial diagnostic for any pulsar, its cosmic birth certificate, and its death warrant written in the language of slowing time. just as a spinning top gradually loses energy to friction and slows down, a pulsar loses energy by flinging out radiation and magnetic winds into space. This loss of rotational energy causes its spin to decay its pulse period to lengthen over millions of years. This spin down is a clock. By measuring the current spin rate and the precise rate of its slowing, you can calculate a theoretical age winding the clock backward to the moment of its birth in a supernova explosion. It's a standard, reliable technique that has been used to date pulsars for over half a century, so the global network of telescopes watched. They timed the arrival of each pulse with atomic precision, measuring the gap between them down to the nanosecond week after week, month after month. They were looking for the tiniest increase in the 57-minute period, the subtle evidence of its inevitable decay. When the results came in, they were met with stunned silence, followed by a frantic dash to recheck the calculations. The numbers were not just unusual, they were heretical. They painted a picture of an object so old its existence felt like a violation of natural law. The spin-down rate was minuscule, almost immeasurably small. This was a celestial gyroscope that was losing its momentum with agonizing slowness. But even that tiny rate of decay, when plugged into the standard equations of stellar evolution, produced an age that was simply staggering. The model suggested this neutron star had been spinning and slowing for at least 200,000 years, and that was where the crisis began. Because our understanding of neutron stars, built on decades of observation and theory, was utterly unambiguous. On one point, the engine that powers a pulsar's radio beams, its colossal magnetic field should not be able to survive that long. A neutron star is born with a magnetic field of unimaginable power, trillions of times stronger than Earth's. It is this spinning supermagnetic field that acts as a cosmic dynamo, accelerating particles and generating the intense beams of radiation we see as pulsars. But this dynamo is not eternal. The intense electrical currents flowing within the star's crust, the very source of its magnetism, eventually dissipate. The field weakens. It decays over time like the charge in a dying battery. According to every model we had, after about 100,000 years, this magnetic field should decay below a critical threshold known as the death line. Beyond this line, the dynamo is too weak. The star no longer has enough power to generate radio emissions. It should fall silent. It should die. This is the pulsar graveyard. A place filled with billions of neutron stars that have crossed the death line, their magnetic fields withered away now, spinning silently and invisibly in the dark. Yet here was an object right in front of us that was not silent. Its spin-down age clearly indicated it was far, far beyond the death line. Based on its rotational properties, this star should have gone quiet when early humans were first migrating out of Africa. It should have been a corpse for at least 10,000 years, probably much longer. It was a zombie, a dead star that was somehow impossibly still pulsing. Its very existence was a paradox, a direct and profound contradiction of the fundamental laws we thought we understood. The implications were terrifying. It meant that either our understanding of magnetic field decay in neutron stars was catastrophically wrong, or some unknown exotic physical process was at play. A process that could keep a star's magnetic heart beating long after it should have flatlined. Or even more bizarrely, a process that could resuscitate a dead one. The scientific community was thrown into a state of controlled chaos. Papers were written, theories were proposed and immediately torn apart. Could it be a completely new type of celestial object? Perhaps a white dwarf with an abnormally strong magnetic field masquerading as a neutron star, or no. The pulse was too regular, too sharp. The physics of a white dwarf couldn't produce such a coherent signal. Could the magnetic field be regenerating itself through some bizarre quantum mechanism in its core? The idea was speculative, bordering on science fiction, with no evidence to support it. Every attempt to explain this zombie with conventional physics failed. Each new calculation only deepened the mystery, reinforcing the sheer impossibility of what we were seeing. The object defied categorization. It was spinning too slowly to be a normal pulsar, yet it was pulsing, which meant it couldn't be a dead one. It was a square peg in a universe of round holes, a single data point that threatened to unravel an entire tapestry of astrophysical theory. We had set out to survey a graveyard expecting to find only silence and relics. Instead, we had found a living ghost. We had stumbled upon a cosmic enigma that questioned the very nature of stellar death. This faint, slow, impossibly persistent whisper from the darkness was not just a new discovery, it was an accusation. It told us that we were missing something fundamental in our story of the cosmos. It was proof that even in the graveyards of the universe there are secrets that refuse to stay buried. The confrontation had begun not with a bang, but with a pulse that echoed every hour, a patient rhythmic heartbeat from beyond the grave, challenging us, daring us to understand. How can a dead star speak? What unknown force could possibly reanimate a cosmic corpse, giving it a voice long after its time had passed? The search for an answer would take us deeper into the bizarre physics of degenerate matter, to the very limits of our knowledge, where the line between life and death for a star begins to blur into something new and altogether more terrifying. The models were broken. Every textbook explanation, every carefully constructed theory of stellar evolution hammered out over decades now lay in ruins before this single defiant point of light. The data had been checked, rechecked, and checked again by independent teams across the globe. There was no error in the observation, no glitch in the machine. The ghost in the constellation of Sagittarius was real. A neutron star, silent for 10 millennia, had inexplicably, impossibly returned to life. For the global community of astrophysicists, this was not just a puzzle, it was an affront to cosmic law. It was as if they had stumbled upon a human skeleton long buried and forgotten, only to watch it sit up, dust itself off, and begin to breathe. The initial shock that had rippled through observatories from Chile to Hawaii now began to recede, replaced by something far more potent, far more dangerous, and far more exciting: the frantic, desperate scramble for an answer. The silence of the void was suddenly filled with a clamour of debate as the world's greatest minds rushed to explain the inexplicable. The theoretical battlefield was now open. On one side of this intellectual chasm, a radical and audacious idea began to take root. It was an idea that whispered of heresy, suggesting that perhaps the problem wasn't that our understanding of neutron stars was incomplete, but that we weren't looking at a neutron star at all. Could this object, this cosmic zombie, represent something entirely new, a previously unknown class of stellar remnant to bridge between the familiar and the utterly alien? Proponents of this view argued that we were witnessing the signature of an object that physics had only ever hinted at in the most esoteric equations. They spoke of quark stars or strange stars, theoretical objects where the crushing gravity is so immense that protons and neutrons themselves are shattered. In this exotic state of matter, the very building blocks of atoms dissolve into a sea of their fundamental constituents, up, down, and strange quarks. Such an object would be even smaller and denser than a neutron star, a hyper-compressed nugget of pure nuclear essence. Its internal structure, a swirling soup of fundamental particles, might possess properties that our current models simply cannot predict. Perhaps its magnetic field isn't generated by the same mechanisms we understand. Perhaps it doesn't decay over time, but instead oscillates, hibernating for eons, before a quantum fluctuation deep within its core brings it roaring back. This was a breathtaking leap of imagination. It was cosmology at its most speculative, bordering on science fiction. But it was a hypothesis born of necessity. If all known rules are broken by a single observation, then perhaps the rules themselves are wrong, or at least incomplete. The pushback, however, was immediate and fierce. The principle of Occam's razor, the idea that the simplest explanation is usually the correct one, is a bedrock of scientific inquiry, and inventing an entirely new type of star to explain one anomalous object struck many as a violation of that principle. Show us the evidence, the skeptics demanded. Where are the other examples? If these quark stars exist, the universe should be littered with them. But there were none. Our zombie stood alone, a celestial enigma without precedent or peer. The theory was elegant, profound, and entirely untestable with our current technology. It remained a ghost story told around the campfires of theoretical physics, a tantalizing possibility lingering at the edge of reason, a reminder that the universe's bestiary might contain creatures far stranger than we have ever dreamed. It was a beautiful idea, but for now it offered no solid ground. A more conservative camp turned their gaze not inward toward the star's exotic core, but outward into the darkness that surrounded it. They asked a different question: what if the star itself was ordinary, and its resurrection was caused by some external trigger? The crime scene, they argued, needed to be investigated for accomplices. The stellar graveyard is not a peaceful place. It is a dynamic, chaotic environment where the dead do not always rest in peace. Perhaps our zombie star was not alone in its cosmic tomb. The most obvious culprit would be a binary companion, another star, or the remnant of one locked in a long invisible dance with our pulsar. For thousands of years, the two could have spiraled in silence, their orbits wide and uneventful. But gravity is a patient hunter. Over millennia, their paths could have tightened, drawing them inexorably closer, until the companion star strayed too near. If this unseen partner were a main sequence star or even a bloated giant, the neutron star's ferocious gravity could have begun to siphon off its outer layers. You must picture it a river of superheated gas, a brilliant streamer of stolen star stuff pulled across the void. This material wouldn't just fall onto the neutron star, it would be funneled by the star's residual magnetic field toward its poles, forming a vast accretion disk. This disk would spin at incredible speeds, a cosmic whirlpool heated to millions of degrees by sheer friction. As this matter crashed down onto the neutron star's surface, it would be like pouring gasoline onto a dying ember. The impact would spin the star up, increasing its rotation, effectively recharging the dynamo that had lain dormant for so long. The sleeping magnetic beast would reawaken, and the lighthouse beams would once again begin to sweep across the cosmos. The pulsar would be reborn not from its own power, but through an act of stellar vampirism. It was a compelling, dramatic narrative, and one that relied on known established physics. We have seen such systems elsewhere in the universe. They are known as X-ray binaries, and they are among the most luminous objects in the sky. But here too, the evidence was stubbornly absent. An accretion disk hot enough to reignite a pulsar would blaze with high-energy radiation, particularly X-rays. Yet when astronomers pointed their most sensitive X-ray telescopes like Chandra and XMM Newton at the zombie's location, they found nothing. Only a profound and unnerving quiet. The space around the pulsar was clean, devoid of the telltale glow of superheated gas. Furthermore, the timing of the pulsar's signal was almost unnaturally stable. If it were being spun up by a messy, chaotic process of accretion, we would expect to see tiny fluctuations, little jitters in the precise rhythm of its pulse, as clumps of matter rained down. Instead, the pulse was as regular as an atomic clock, a sign of a pristine, isolated system. The search for an accomplice had turned up no fingerprints, no murder weapon, no motive. The theory of a hidden companion, while plausible, was a beautiful story, without a single shred of supporting evidence. The zombie, it seemed, had acted alone. The source of its unnatural life had to come from within, and so the investigation turned back to the star itself. If there was no new physics and no external trigger, then there had to be something fundamentally misunderstood about the nature of neutron stars themselves. The core of the problem was the magnetic field. For decades, the prevailing wisdom was that a neutron star's magnetic field was a fossil field, a relic, a ghost of the magnetic field that belonged to the massive star that created it. When the star collapsed, its magnetic field was trapped and amplified, frozen into the neutron star's crust like iron filings in ice. And like any fossil, it was supposed to be static, decaying slowly over millions of years as electrical currents in the crust dissipated. A 10,000-year-old pulsar should have a magnetic field far too weak to generate the radio beams we were observing. Its engine should have sputtered out long ago. But what if the fossil field theory was wrong? What if the field wasn't a relic at all? What if it was being actively and continuously generated by a dynamo deep within the star's core, an engine that never truly dies? This was the question that led scientists to a class of objects that had until then been considered the brutish outliers of the neutron star family. They are the cosmic tyrants, the magnetic monsters of the galaxy. They are called magnetars. The concept of a magnetar stretches the physics of a neutron star to its absolute breaking point. A typical neutron star has a magnetic field that is already 1 trillion times stronger than Earth's. A magnetar's field is 1,000 times stronger than that. It is the most magnetic environment we know of in the entire universe, a place where the laws of physics themselves begin to warp and fray. If you were to venture within 1,000 kilometers of a magnet, or its magnetic field would rip you apart atom by atom. The very chemistry of your body would cease to function. It is a force of nature so extreme that it defies easy analogy. It is a gravitational singularity's magnetic cousin, and crucially, this colossal magnetic field is not believed to be a fossil. It is thought to be generated by a powerful self-sustaining dynamo, a convective engine churning within the star's superfluid core in the first few seconds of its life. Imagine the interior of a newborn neutron star. It's a chaotic inferno, a sea of neutron-rich matter heated to billions of degrees, spinning hundreds of times per second. If the conditions are just right, a perfect combination of extreme temperature and rapid rotation, a runaway feedback loop can occur. The churning convective motion of the stellar fluid acts like a cosmic generator, amplifying tiny seed magnetic fields into universe-altering behemoths in a fraction of a second. This process transforms a mere neutron star into a magnetar loading its magnetic field with an incomprehensible amount of energy. For the first few thousand years of its life, a magnetar is a violent, unpredictable beast. The immense magnetic field stresses and twists the star's solid crust. Eventually, the crust cracks, releasing the stored energy in cataclysmic starquakes. These events unleash blasts of gamma rays and X-rays so powerful they can affect Earth's atmosphere from halfway across the galaxy. We have witnessed these tantrums, these cosmic flashes of rage, and they confirm the terrifying power these objects command. This was the leading theory on the table. Our zombie wasn't just any old neutron star, it was a magnetar. But this solution created a new, even deeper puzzle. Magnetars as we knew them were famous for being loud, violent, and young. They announced their presence with brilliant flares of high-energy radiation. Our object, by contrast, was old, quiet for millennia, and broadcasting in the comparatively gentle whisper of radio waves. It didn't fit the profile. It was like finding a dormant volcano that, instead of erupting with lava and ash, had begun to hum a soft, steady tune. The discrepancy was glaring. The community was torn. At scientific conferences, the arguments grew more heated. Whiteboards were filled with complex equations, then angrily erased and filled again. Proponents of the magnetar hypothesis argued that we had only ever witnessed the youthful phase of a magnetar's life. We had never seen an elderly one. Perhaps after 10,000 years, the initial violent rage subsides. The star quakes become less frequent, the gamma ray bursts cease. The object enters a new, quieter phase of existence. This new theory, a modification of the magnetar model, was both elegant and profound. It suggested that the magnetic field of an ancient magnetar doesn't simply fade away. Instead, the energy stored within it finds a new way to escape. The colossal tangled magnetic field lines outside the star could slowly untwist and reconfigure themselves. This process, known as magnetic reconnection, could release energy in a far more controlled, sustained manner than a violent starquake. This slow, steady release of magnetic energy could gently heat small spots on the neutron star's surface, creating hotspots at the magnetic poles. These hotspots would be hot enough to boil off particles, creating the plasma needed to generate the lighthouse beams of a pulsar. The magnetar, in its old age, had learned a new trick. It had transitioned from a raging explosive monster into a persistent pulsing zombie, powered not by rotation, but by the slow, inexorable decay of its own monumental magnetic field. It was a stunning synthesis of ideas. It explained the object's age, its long silence, and its sudden reawakening, all without invoking new physics or unseen companions. It suggested that a pulsar's life might not be a simple story of birth and slow decline. For some, it could be a story of multiple acts of violent youth, quiet middle age, and a strange magnetically powered afterlife. This ancient magnetar model quickly became the frontrunner, the most plausible explanation for the impossible star. It reframed the zombie not as an anomaly that broke the rules, but as a messenger from an undiscovered country, revealing a new chapter in the lives of the most extreme objects in the universe. It suggested that there might be a hidden population of these sleeping magnetic zombies scattered throughout the Milky Way, their pulses temporarily silenced, waiting for their internal magnetic engines to stir them from their slumber. We had simply been lucky enough to be watching when one of them woke up. But a theory, no matter how beautiful or compelling, is not the same as proof. It is a map of a territory that has not yet been explored. The ancient magnetar hypothesis made specific testable predictions. If the pulsar was indeed powered by a decaying magnetic field, its behaviour should be subtly different from that of a normal rotation-powered pulsar. The rhythm of its pulse might change in unique ways, its radio emission might have a peculiar signature, a magnetic accent that could betray its true nature. The challenge was laid down. The theory provided a target, a set of clues to look for. Now, astronomers had to return to their telescopes not just to watch the zombie, but to interrogate it, to force it to confess the secret of its resurrection. For if this object truly was an ancient magnetar, it was more than a curiosity. It was a Rosetta Stone, a key that could unlock the deepest mysteries of magnetism, matter, and the hidden lives of the cosmic dead. The hunt for that definitive proof was on a quest that would push our technology and our ingenuity to the very edge. To call it a magnetar, then, is to trade one mystery for another, a far deeper and more perplexing one. We may have found a name for our ghost, but we have absolutely no idea how it manages to keep rattling its chains. The very laws of physics as we understand them suggest this phantom should have faded into silence millennia ago. A magnetar's power, its entire identity, is woven from the raw force of its magnetic field, a field so violent it can tear atoms apart and warp the very fabric of space-time. But this cosmic engine is not perpetual. Like any great furnace, it consumes its own fuel. The colossal electrical currents swirling within the neutron star's crust, the very source of its magnetism, face a relentless opposition. They generate immense heat, they drive powerful particle winds, and they bleed their energy out into the unforgiving vacuum of space. This process, a slow but inexorable decay, should have tapered off over thousands of years, reducing the once mighty magnetar to a quiet conventional neutron star. Our zombie, however, refuses to follow the script. Its pulse, though faint and slow, is a stubborn rhythmic protest against the expected silence. It beats with a strength that defies its age, forcing us to ask a question that strikes at the heart of stellar physics. How can a magnetic field of this magnitude endure for so long? What secret mechanism hidden deep within that hyperdense core is keeping this stellar ghost alive? The answer, if it exists, is buried in a place more alien than any distant world, a realm governed by forces and states of matter that challenge the limits of our imagination. To find it, we must journey inward past the star's solid crystalline crust, a metallic lattice, a mile thick and billions of times stronger than steel. Beneath this impossibly rigid shell, we descend into the outer core. Here the pressure is so immense that the very concept of an atom ceases to have meaning. Protons and electrons are crushed together in a violent act of cosmic alchemy, forging a sea of pure neutrons. But this is no simple uniform fluid. It is a substance operating at the bleeding edge of quantum mechanics. The neutrons, freed from their atomic prisons, have entered a state known as superfluidity. Imagine a liquid with absolutely zero viscosity, a substance that once set in motion would flow forever without losing a single drop of energy to friction. It is a perfect frictionless ocean that churns in the heart of the dead star. Within this neutron superfluid, however, swim other even stranger things. A small fraction of protons and electrons survive the crush, and they too undergo a quantum transformation. They become superconductors, forming a river of electrical charge that can flow without any resistance, a perfect current that could persist for longer than the current age of the universe. Here in this bizarre quantum soup of a frictionless superfluid and a resistance-free superconductor lies the first clue to our zombie's longevity. In a conventional model, a magnetar's field is anchored in its solid crust. As the crust cools and the star ages, this field should dissipate its energy, bleeding away. But what if the true heart of the dynamo lies deeper? Some physicists now theorize that the magnetic field is not merely a feature of the crust, but is instead fundamentally woven into the interplay of these quantum fluids in the core. The swirling neutron superfluid moving without friction could create countless microscopic vortices, tiny perfect whirlpools of matter. As these vortices move, they can drag the superconducting protons along with them. This interaction, a dance between the uncharged, frictionless neutrons and the charged, resistance-free protons, could generate a self-sustaining electrical current. It would be a dynamo of almost perfect efficiency, a gravitational gyroscope where the rotational energy of the star itself is continuously converted into magnetic power with almost no energy loss. The field wouldn't be decaying because it wouldn't be a relic of the star's birth. It would be an active living system constantly regenerated by the quantum mechanics of its own core. The star isn't just a cooling ember, it's a colossal quantum battery slowly discharging over an immense timescale we have yet to fully comprehend. This model presents a stunningly elegant solution, painting a picture of a star whose internal physics are far more dynamic than we ever suspected. Yet it also opens up new avenues of complexity. This core dynamo theory suggests that the magnetic field we observe is merely the tip of a much larger, more powerful iceberg, a vast internal magnetic structure whose true strength is hidden from our view. The field lines generated deep within must then thread their way up through the star's outer layers and burst through the solid crust. The crust in this scenario acts less like an anchor and more like a gatekeeper, a rigid barrier that shapes and directs the magnetic fury from below. This introduces a volatile and potentially violent element to the star's life. Over time, the immense magnetic stress from the core could build up beneath the crust, twisting and deforming the crystalline lattice. The tension would grow for centuries, for millennia, until the crust can no longer contain the pressure. The result would be a starquake, an explosive event of unimaginable power. The solid surface of the star would shatter and rearrange itself, a catastrophic realignment that would be thousands of trillions of times more powerful than the largest earthquake in Earth's history. Such a cataclysm would do more than just shake the star. It would fundamentally reconfigure the external magnetic field. In a flash, tangled magnetic lines from the interior could erupt onto the surface, effectively recharging the magnetar's observable field. This could explain our zombie's surprising vitality. Perhaps what we are witnessing is not a star that has miraculously resisted decay, but one that has recently undergone a rejuvenation. 10,000 years ago, it might have been fading, its pulse weakening as expected. Then a titanic starquake ripped through its crust, injecting a fresh burst of magnetic energy into its magnetosphere and resetting the clock on its decay. The slow, steady pulse we detect today would be the lingering heartbeat of that ancient violent event. This theory transforms our perception of the object from a static, slowly dying relic into something dynamic and unpredictable. It suggests that these zombie stars might not be in a state of gentle decline, but rather exist in a long cycle of dormancy punctuated by brief, furious awakenings. We just happen to be catching this one in the long, quiet aftermath of its last great upheaval, a period of calm before the next storm inevitably brews in its quantum heart. This idea is both compelling and terrifying, suggesting that even the deadest stars in the cosmos might harbour a capacity for sudden, astonishing violence, their quiet graveyards capable of erupting with the energy of 1,000 suns. But beautiful theory is just a story until it can be tested against the cold, hard light of observation. And here we face the second great challenge our zombie star presents. The physics we've described are happening in a laboratory that is hundreds or thousands of light years away in an object barely 20 kilometers across. Peering into the heart of a neutron star is, without exaggeration, one of the most difficult observational tasks in all of astronomy. The signals we seek are infinitesimally faint whispers from a cosmic ghost that are easily lost in the roaring noise of the universe. The slow, 20-minute pulse of our object is a perfect example of this dilemma. For decades, our radio surveys were designed to find the rapid-fire beacons of young, energetic pulsars. We were hunting for hummingbirds, and in doing so we built nets that allowed the slow, lumbering tortoises of the cosmos to slip right through unnoticed. Discovering this one object was a stroke of luck, a fortunate glance in the right direction at the right time. Finding more of them, and studying them in the detail required to test our theories, demands a fundamental shift in both our technology and our strategy. We can no longer simply scan the sky for the obvious. We must now learn how to listen for the near silence, to search for the barely perceptible rhythms of these ancient dying beasts. To do this, we need new eyes and new ears on the universe. The radio telescopes of the past, even the giants that have served us for half a century, are not sufficient for this new quest. We are pushing the absolute limits of what is possible. Verifying the quantum dynamo theory requires more than just detecting a pulse. It requires dissecting it. We need to measure subtle changes in the timing of the pulse, tiny deviations, glitches or anti-glitches that could betray the churning of the superfluid core beneath. This is akin to trying to diagnose a patient's heart condition by measuring the trembling of a single hair on their head. We also need to analyse the polarisation of the radio waves, the specific orientation of the light as it travels toward us. The way this light is twisted as it passes through the star's magnetosphere can provide a map of the magnetic field structure, revealing whether it is the simple, orderly field of a cross-anchored magnet or the more complex tangled mess that might erupt after a starquake. These are measurements of breathtaking precision, demanding a level of sensitivity that is currently beyond our reach. We are in essence trying to perform cosmic archaeology on an object that is actively trying to hide its secrets from us, shrouding itself in a cloak of faintness and distance. The solution lies in building bigger. Not just marginally bigger, but radically paradigm-shatteringly bigger. The next generation of radio astronomy is taking shape right now in the quiet deserts of South Africa and Australia. It is called the Square Kilometre Array, or SKA. When complete, it will not be a single dish, but a continent-spanning network of thousands of antennas all working in concert. Together they will form a single virtual telescope with a collecting area of 1 full square kilometre, making it 50 times more sensitive than any radio instrument ever built by humankind. The SKA will be an unparalleled machine for hunting ghosts. It will be able to survey the sky with a speed and depth that will make our current efforts look primitive. It will have the power to detect the feeble radio whispers from zombie magentars across our entire galaxy, transforming them from a singular anomaly into a whole population we can study. With the SKA, we can monitor these objects for years, patiently waiting for the subtle timing variations that could prove the existence of a superfluid core. We can map their magnetic fields with exquisite detail, searching for the telltale signs of a recent starquake. We can finally begin to answer the question of whether our zombie is a unique freak of nature, or the first glimpse of a vast hidden graveyard of slowly pulsing stellar remnants that fills the Milky Way. But radio waves only tell part of the story. The immense energy of a magnetar is not just released as a gentle radio pulse. Its magnetic field also heats the star's surface, causing it to glow faintly in high-energy X-rays. Observing this X-ray emission is another crucial piece of the puzzle. The temperature of the star's surface and the presence of localized hotspots can tell us how the magnetic field is interacting with the crust. A smooth, uniform temperature might suggest a stable, ancient field. A surface dotted with mysterious hot patches, however, could be the thermal scars left behind by a recent violent magnetic eruption, the still glowing embers of a colossal starquake. These X-ray signals are even fainter than their radio counterparts, a trickle of high-energy photons against a bright, noisy background. To capture them, we need to go to space, deploying a new generation of X-ray observatories with mirrors larger and detectors more sensitive than ever before. Telescopes like the proposed Athena Observatory by the European Space Agency are designed for exactly this purpose. Orbiting high above the distorting effects of Earth's atmosphere, Athena would be able to stare at our zombie star for days or weeks on end, slowly accumulating the precious few X-ray photons that make the journey across the light years. It would act as a cosmic thermometer, taking the temperature of a ghost to determine how and when it died, or if it was ever truly dead at all. Ultimately, to truly confirm the most exotic of these theories, we may need to listen for something else entirely not light, but a whisper from the fabric of space-time itself. The theories of churning superfluid vortices and catastrophic starquakes predict that these events should not be silent. They should be accompanied by a faint but distinct hum of gravitational waves, ripples in the geometry of the universe. A starquake in particular would deform the star from a perfect sphere, causing it to wobble as it spins. This wobble would radiate gravitational waves, a unique signature of the violence unfolding within. Detecting such a signal would be the ultimate proof, a direct observation of the internal mechanics of a neutron star. Our current gravitational wave observatories like LIGO and Virgo are most sensitive to the violent collisions of black holes and neutron stars. They are listening for the cosmic cymbal crash. To hear the faint continuous hum of a single wobbling zombie star, we would need future even more sensitive detectors, perhaps space-based observatories like LISA. It is a monumental challenge pushing technology to its absolute breaking point. But it is a challenge we must embrace, because the answers we seek are not just about one strange star. They're about the fundamental nature of matter under pressures and densities that we can never hope to replicate here on Earth. This single stubborn pulse, this refusal to fade away, has become a beacon illuminating the dark frontiers of physics. It is a siren call from a quantum realm, daring us to build the tools we need to come and explore, to venture into the heart of the zombie and uncover the secrets of its impossible life. The theories are tantalizing, the physics extraordinary, but they remain ghosts themselves until we can anchor them to observation. The quest now moves from the blackboard to the telescope, from the realm of pure thought to the hard, unforgiving reality of the hunt. And so the paradox remained hanging in the cosmic dark like an unanswered question whispered between the stars. On one side, the immutable laws of physics drawn from decades of observation, which told us our ghost star should be silent, its rotational energy long since spent its lighthouse beam extinguished 10 millennia ago. On the other, the faint undeniable pulse, a heartbeat defying the finality of the cosmic graveyard, a signal that refused to accept its own eulogy. The theories we had explored were a testament to human ingenuity, a sprawling map of maybes and what-ifs. Perhaps it was a cosmic vampire siphoning life from an unseen companion, a process of accretion reigniting its fury in sporadic stolen bursts. Perhaps it was something far stranger, a crack in our understanding of physics itself, a new form of matter decaying in its core, keeping the embers warm long after the fire should have died. Each hypothesis was a bold leap of imagination, yet each struggled under the weight of the evidence or lack thereof. There was no detectable companion, no telltale signature of infalling gas, no exotic radiation to hint at physics beyond our grasp. The clues felt like disconnected fragments of a shattered mirror, each piece reflecting a sliver of the truth, but failing to show us the whole, breathtaking picture. The global community of astronomers, once divided into camps, championing their preferred explanations, began to realize that the solution might not be a single elegant answer. The truth they suspected was not a lightning strike of revelation, but a slow dawn, a convergence of ideas. The real breakthrough would not come from a single telescope, but from a machine that could build universes. Inside the climate-controlled sanctums of supercomputing centers, a new kind of exploration was underway. Here scientists became digital gods, forging a ghost star not of matter, but of mathematics inside silicon minds. They could dictate its birth, giving it any mass, any spin, any temperature they desired, all with lines of code. They built a virtual laboratory where the fundamental forces of nature were the only unbreakable rules, a place where they could compress 1 billion years of cosmic evolution into a single frantic afternoon of computation. These simulations were our time machines, allowing us to witness the entire lifespan of a neutron star, to watch it cool, to see its spin decay, and crucially to observe how its colossal magnetic field would warp and weaken over eons. This was where the first glimmers of our answer began to emerge. The initial models, based on a typical run-of-the-mill neutron star, all confirmed what we already knew. They lived, they spun, they pulsed, and then inexorably they crossed that theoretical death line and fell silent. The simulations were a perfect reflection of our own confusion. They created a graveyard of quiet, cold relics, not a single persistent zombie. The problem wasn't with the physics in the machine. The problem was with the assumptions we were feeding it. We had been modelling the average, the expected, the common. But what if this star was never common to begin with? What if its birth in the heart of a supernova, far more violent than most, had endowed it with an extraordinary gift, or perhaps a curse? The teams began to tweak the initial conditions to push the parameters into the realm of the extreme. They dialed up the star's initial magnetic field not by a little, but by orders of magnitude, forging a star born not just as a pulsar, but as a magnetar, a true monster. A magnetar is a neutron star with a magnetic field so potent, so terrifyingly strong, It defies earthly comparison. A simple kitchen magnet produces a field of about 100 Gauss. A hospital MRI a powerful 10,000. A typical neutron star boasts a field of 1 trillion Gauss. But a magnetar, the beast they were now creating in their simulations, begins its life with a field of 1 quadrillion Gauss, a 1 followed by 15 zeros. This is a force so powerful it could wipe a credit card clean from halfway to the moon. A field so intense it literally distorts the shape of atoms themselves, stretching them into thin needles. We had always considered magnetars and pulsars as different evolutionary paths cousins in the neutron star family. But the simulations were painting a new unified picture. They showed that if you start with this level of magnetic fury, you begin with a far greater reservoir of energy. It's like comparing a flickering candle to a colossal bonfire. Both will eventually burn out, but the bonfire born of a much larger fuel source will leave behind glowing embers that stay warm for an immensely longer time. This primordial inheritance of magnetic violence was the first pillar of the solution. Our zombie star wasn't just a standard pulsar that refused to die, it was likely an ancient faded magnetar. Its ferocious youth had endowed it with such an extreme magnetic and rotational energy budget that even after billions of years after its magnetic field had decayed by a factor of 1,000 from its peak, there was still enough residual power to weakly energize its magnetosphere. The death we calculated for it based on the physics of a normal pulsar was a profound underestimation. We had been measuring its final breaths without ever appreciating the sheer scale of the lungs it was born with. The pulses we were seeing were the faint magnetic ghosts of its former cataclysmic glory. But even this wasn't enough to fully explain the mystery. A powerful beginning could explain a longer life, but the signals were not just weak. They were intermittent, sporadic, almost hesitant. The star seemed to be flickering, not just fading. This pointed to the second pillar of the emerging theory, a revelation that would force us to rewrite the textbooks on how these incredible objects actually age. Our models of magnetic field decay we were discovering had been too simple, too clean. We had pictured the field fading away smoothly and predictably, like the sound of a struck bell gently diminishing into silence. The universe, however, is rarely so tidy. The new, more sophisticated simulations began to incorporate the complex physics of the neutron star's crust. This isn't a crust in any terrestrial sense. It is a crystalline lattice of atomic nuclei, a solid metallic structure 10 million times stronger than steel, held together by the crushing force of gravity. And deep within this crystalline armour, the magnetic field is not a simple uniform entity. It is a tangled, chaotic web of magnetic flux tubes, like immense bundles of invisible wires, plunged into the star's superconducting interior. As the star ages and spins down, these flux tubes are meant to drift outwards and dissipate, carrying the field's energy away with them. This is the process of decay. But the simulations began to show something fascinating. In certain conditions, particularly in a crust that is unusually pure or has a specific crystalline structure, these flux tubes can become pinned. They get stuck snagged within the crustal lattice, unable to escape as quickly as our older theories predicted. It acts like a breaker cosmic anchor holding the magnetic field in place, dramatically slowing down the rate of decay. The star's death is postponed not for thousands, but perhaps for millions of years beyond its expected expiration date. Its magnetic heart, instead of bleeding its energy out into space, retains it, preserving a faint echo of its power deep within. So now we had two crucial pieces of the puzzle: a star born with an exceptionally powerful magnetic field, and a star whose crust was acting like a faulty dam, preventing that field from draining away as quickly as it should. It explained the persistence, the sheer longevity. It explained why an object so ancient still possessed the minimum magnetic strength to generate a radio beam. But it still didn't fully account for the zombie's most unnerving behaviour, the flickering on-again, off-again nature of its pulse, the very behaviour that had eluded our detection for so long. This led to the third and perhaps most dramatic part of the solution, the element that truly earns it the name zombie. The star wasn't just fading slowly, it was being reawakened. Imagine the immense stresses building up within that crystalline crust over thousands of years. The star's rotation is slowing, but its interior, a frictionless superfluid, may not be slowing at the same rate. This creates a strain between the interior and the solid crust, a tension that grows and grows until the breaking point is reached, and when it breaks, the result is a starquake, a seismic convulsion of unimaginable violence that ripples across the star's surface in seconds. The energy released in a single one of these starquakes can be greater than what our own sun will radiate in 100,000 years. This is not a gentle shudder, it is a cataclysm that fractures the star's armour, and in doing so it dramatically reconfigures the magnetic field lines that are pinned within it. Suddenly tangled, submerged magnetic fields can be jolted, snapping out into the magnetosphere. For a brief period, perhaps a few weeks, a few years, the star's faint lighthouse beam is reignited, or at least significantly boosted. The quake acts like a defibrillator, shocking the dying heart back into a temporary rhythmic beat. The zombie rises, it pulses, it broadcasts its unlikely existence across the void, and then as the new field configuration settles, it fades back into dormancy, back into near silence. It lies in wait for centuries or millennia until the stresses build once more, and another quake shudders through its core, triggering another brief resurrection. We now believe this is what our telescopes stumbled upon. We didn't just find an old star. We caught it in the immediate aftermath of one of these resuscitation events, a fleeting moment of activity in an existence now defined by immense periods of quiet. There is another complementary possibility for these reawakenings. Even the empty space between stars is not perfectly empty. It is filled with the tenuous interstellar medium wisps of gas and dust. For a neutron star travelling through a slightly denser patch of this medium, its immense gravity could begin to pull in this surrounding material. It wouldn't be a dramatic continuous flood like in a binary system, but a slow, almost imperceptible drizzle of matter falling onto its magnetic poles. This trickle of accreted material heated to millions of degrees as it impacts the surface can create localized hotspots, temporarily energizing the magnetosphere and generating a weak flickering beam of radio waves. The star isn't just surviving on its inheritance, it's occasionally scavenging for scraps, feeding on the void itself to keep its pulse alive. When you weave these three threads together, the full, breathtaking tapestry of the solution is finally revealed. You have a star born a monster, a magnetar with a vast energy reserve. You have a star with a specialized crust that dramatically slows the decay of its magnetic life force, and you have a star subject to violent internal upheavals and potential external feeding events that periodically jolt it back from the brink, reanimating its radio beam for brief glorious moments across cosmic time. The central conflict is resolved, the mystery is solved, and in its resolution we are forced to fundamentally reframe our initial dramatic declaration. This neutron star was never truly dead for 10,000 years. Our concept of death, a binary switch between on and off, is a human-scale idea that simply doesn't apply to these objects. The star wasn't dead. It was in a state of profound dormancy, an ultra-slow hibernation so deep, so quiet, that it was indistinguishable from death to our fleeting observations. Its life is not a steady decline into silence, but a long drawn-out twilight punctuated by startling flashes of memory, a series of echoes from its own violent youth. This discovery has utterly reshaped our understanding of the final stages of stellar evolution. The pulsar death line is not a wall, but a porous boundary, a misty shore from which some inhabitants can, it seems, occasionally return. It implies that the cosmos is littered with these hibernating relics, a silent population of zombie stars we never knew existed. We had been scanning the heavens for steady rhythmic heartbeats, and in doing so, we missed the millions of sleepers waiting for a cosmic quake, or a wisp of gas to briefly stir them. They are a new class of celestial object hiding in plain sight, their faint intermittent cries for attention lost in the overwhelming noise of the galaxy. We have found one by a staggering stroke of luck. A single, inexplicable pulse from an object that should have been quiet was all it took to pull back the curtain on a vast undiscovered country. The question that once kept us awake at night, how could this one star still be pulsing, has been answered. But it has been replaced by a new question, one far grander and more profound in its implications. If one exists, how many more are out there sleeping in the dark, waiting for the right moment to flicker back to life and tell us the story of the universe's secret survivors? The search has now truly begun. And so the phantom is explained. The ghost in the machine is given a name, a history and a mechanism born from the most violent and exotic physics imaginable. We have journeyed across 10,000 years of silence, tracing the ghostly echo of a star that by all rights should be inert, a crystalline monument to a violent past. What began as an anomaly, a single maddening point of light blinking where none should exist, has resolved into a profound revelation. It has forced us to confront the unsettling but thrilling truth that even in the celestial graveyard, death is not always the end. The story of this impossible object is not just the biography of a single star. It is a new chapter in our own cosmic education, a lesson written in gamma rays and radio waves teaching us that the universe's imagination will always exceed our own. We began this journey with a simple established truth, the pulsar death line. It was a concept as fundamental to stellar astrophysics as gravity itself, a theoretical border drawn across the cosmos. On one side, vibrant spinning neutron stars sweeping their lighthouse beams across the void. On the other, the profound silence of the stellar dead, their rotational energy spent, their magnetic dynamos stilled. We built our models on this foundation. We aimed our telescopes with this certainty. We wrote our textbooks enshrining this principle as a final immutable law. For decades, this line held firm a reliable demarcation between the living and the dead. It provided a neat, predictable conclusion to the otherwise tumultuous life of a massive star. Yet this one object, this stubborn whispering corpse, has erased that line. It has demonstrated with its patient haunting pulse that the boundary is not a wall but a veil, and that under the right circumstances that veil can be pierced. The implications of this are staggering, rippling through every facet of high-energy astrophysics. We are now forced to reconsider the very nature of a magnetar's death. Before we envisioned a relatively straightforward decay, a colossal magnetic field, the most powerful in the universe, gradually and uniformly fading into obsolescence. We pictured a titan simply growing tired, its billion Tesla fury slowly mellowing over millennia, until it could no longer power the particle winds that made it shine. This zombie star teaches us that the process is infinitely more subtle, more complex, and more beautifully chaotic. The death of a magnetar is not a simple fading of the light, it is a metamorphosis. The dominant simple dipolar field, the straightforward north-south magnet we learn about in school, may indeed weaken and fall below the threshold for radio emission. This is the moment of its first death, the moment it crosses the death line and disappears from our conventional surveys. But beneath this placid surface, a hidden storm can continue to rage. The star's magnetic heart does not stop beating, it just changes its rhythm. More complex tightly wound magnetic geometries, quadrupolar, octopolar fields, tangled loops and violent localized knots of immense power can persist deep within the star's crust and magnetosphere. These are the embers of the ancient fire, a reserve of magnetic energy that doesn't contribute to the main pulsar beam but remains terrifyingly potent. For thousands of years, these hidden fields can churn and twist, stressing the star's adamantium-hard crust. They are a form of stored violence, a gravitational promise of a future outburst. And then, as we have now witnessed, a critical threshold is reached. The crust, strained beyond its limits, finally cracks. This is not the starquake of a young, vibrant magnetar, but something else entirely, a post-mortem convulsion. This event, this cracking of a tomb, reconfigures the magnetic field on a colossal scale. Those deep, tangled, multipolar fields are violently dredged to the surface. In a cosmic instant, the star's external magnetic topology is rewritten. The quiet graveyard suddenly hosts a resurrection. The star's rotational axis may be realigned, or the magnetic poles themselves might be reborn in new locations energized by this fresh injection of power from the star's interior reservoir. This restructuring doesn't necessarily restore the star to its youthful glory, but it does just enough. It provides the necessary voltage to once again accelerate particles above the poles, to reignite the particle winds, and to spin up the celestial blowtorch that generates the radio waves we detect. The lighthouse is switched back on, not by reigniting the main furnace, but by striking a match with the residual fuel left in the lines. The star begins to pulse again, a faint, slow, ghostly beat from beyond the grave. This is the new reality we must now incorporate into our models. The life cycle of a magnetar is not linear. It can be cyclical, punctuated by periods of death and rebirth. The death line is not an endpoint, but a potential hibernation state. This single discovery has transformed our view of the neutron star population. We are now confronted with the possibility of a vast hidden graveyard of slumbering objects, a subpopulation of stellar remnants we had prematurely classified as extinct. These are the zombies, the undead, and for all we know, they could vastly outnumber their living brethren. They are the quiet majority waiting for some internal trigger to stir them from their millennia-long slumber. Every silent, isolated neutron star we had previously dismissed as a cold cinder is now a suspect. Each one is a potential ghost waiting to happen a puzzle box of tangled magnetic fields that could at any moment spring back to a semblance of life. This realization launches a completely new kind of hunt, a form of celestial archaeology aimed at finding the walking dead. Our entire search strategy has to be redesigned. Previously, radio astronomers conducting large-scale surveys of the sky would often filter out signals that were too slow, too faint, or too sporadic. We were hunting for the powerful clockwork pulses of young, energetic pulsars. Our algorithms were biased towards the living. We were in essence deliberately deaf to the whispers of the dead. Now we must retrain our electronic ears. We must learn to listen for the slow, laboured breathing of an ancient star for a heartbeat that might only appear once every few seconds or even minutes. This requires a fundamental shift in both technology and philosophy. It demands more sensitive telescopes, longer observation times, and smarter, more patient algorithms capable of sifting through cosmic noise to find a signal that is faint, intermittent, and utterly strange. The hunt begins in two primary arenas. First, the archives. For more than half a century, we have been recording the radio sky, creating a vast digital library of the cosmos. Buried within that petabyte-scale mountain of data, how many other zombie stars might be hiding? How many signals did we record flag as interference or instrumental noise and discard simply because they didn't fit our preconceived notions of what a pulsar should look like? Astronomers are now launching ambitious projects to reanalyze this historical data, applying new machine learning techniques trained to look for exactly these kinds of slow, ghostly pulses. It is a painstaking process, like searching an entire library for a single misplaced word. But the potential reward is immense, the discovery of a whole class of objects that have been staring us in the face for decades, their messages simply waiting for us to learn their language. We could find that our zombie is not a freak of nature, but the first citizen of a vast undiscovered country. Second, the new surveys. Telescopes like the Square Kilometre Array coming online in the near future will survey the sky with unprecedented sensitivity and speed. These next-generation instruments are perfectly suited for this new search. They can stare at patches of the sky for thousands of hours, accumulating data with a depth we've only dreamed of. They will be our ghost-hunting machines capable of detecting the faintest of celestial whispers. We will point them towards the graveyards, the centres of old supernova, remnants the galactic halo regions far from the stellar nurseries where young pulsars are born. We will be deliberately searching for silence and then listening intently for the one faint sound that breaks it. Each new detection will be another data point, another piece of the puzzle. We will be able to map their population to understand their birth rates and to determine just how common this resurrection phenomenon truly is. Is it a once-in-a-billion-year fluke, or a standard if rare phase in the final chapter of every magnetar's life? Beyond simply counting them, each new zombie star will be a unique laboratory for fundamental physics. The conditions within these objects are unlike anything we can ever hope to replicate on Earth. The crust of a neutron star is the strongest material in the universe, a crystalline lattice of atomic nuclei crushed together under unimaginable pressure. Understanding how and why it cracks under magnetic stress gives us a direct window into the physics of superdense matter. We can test our theories of the nuclear strong force, the glue that binds atomic nuclei together, under conditions of extreme duress. The behaviour of this crust, its sheer strength and breaking strain, is governed by the laws of quantum mechanics playing out on a macroscopic scale. Every tremor, every crack, every subsequent outburst from one of these objects is an experiment being conducted for us, a stress test of matter at the very edge of physical possibility. Furthermore, the magnetic fields themselves are a frontier of knowledge, A field 1,000,000,000,000 times stronger than Earth's is not just a scaled-up version of a refrigerator magnet. In such an environment, the vacuum of space itself behaves differently. According to the laws of quantum electrodynamics, the vacuum is not empty, but a seething foam of virtual particles constantly popping in and out of existence. An ultra-strong magnetic field can polarize this vacuum, distorting it, changing the way light propagates through it. This phenomenon, called vacuum birefringence, has been predicted by theory for almost a century, but has never been definitively observed. A zombie star with its complex and evolving magnetic field could be the perfect place to finally witness this. By studying the polarization of the light coming from the star, we might be able to see the ghostly imprint of the vacuum itself being twisted by the magnetar's power. This would be a monumental confirmation of our understanding of quantum field theory and the strong field regime. These objects also provide a new tool for probing the enigmatic phenomenon of fast radio bursts, or FRBs. These are brilliant millisecond-long flashes of radio waves from distant galaxies, and their origin remains one of the greatest unsolved mysteries in astronomy. The leading theory is that many of them are produced by magnetars. Our zombie star, with its dramatic tale of magnetic restructuring and violent energy release, adds a crucial new piece to this puzzle. Could some FRBs be the product of similar events but on a much grander scale? Could they be the birth cries of a zombie star in another galaxy? The flash of light produced when the tomb of a dead magnetar is violently cracked open. By studying the local, much tamer version of this process, we can build more accurate models for what might be happening billions of light years away, connecting the physics of our own galactic neighbourhood to the most powerful and mysterious explosions in the distant universe. Ultimately, this journey into the heart of a dead star brings us back to a fundamental human question. How well do we truly know the universe we inhabit? We are pattern-seeking creatures. We build models, we draw lines, we establish laws. We seek to place the magnificent chaos of the cosmos into neat, understandable boxes. It is a necessary part of the scientific process, the foundation upon which we build our understanding. But every so often the universe sends us a messenger, an impossible planet, a paradoxical black hole, or a star that refuses to stay dead to gently or sometimes violently remind us that our boxes are too small. This zombie star is one such messenger. It is a cosmic epitaph that continues to write itself, a testament to the fact that even in death the universe retains its capacity for astonishment. It tells us that the cosmos is not just a collection of objects to be catalogued, but a dynamic evolving stage where the rules themselves can have exceptions. It reminds us that our knowledge is always provisional, a single frame in a movie whose full plot we cannot yet fathom. The discovery is a profound lesson in scientific humility. It forces us to go back to our blackboards, to question our most basic assumptions, and to embrace the discomfort of the unknown. And in that discomfort we find the true engine of discovery. It is the grit in the oyster that creates the pearl. The thrill of science is not in confirming what we already know, but in confronting what we thought was impossible. As you look up at the night sky, at that serene tapestry of quiet, distant lights, remember this story. Remember that among those placid points of light are objects of unimaginable violence and incomprehensible density. There are stellar furnaces, gravitational tombs, and lighthouses spinning faster than a kitchen blender. And now we know there is something else. There are ghosts. There are sleeping giants biding their time in the dark, their magnetic hearts still holding a latent, furious energy. We have found one. The great, exhilarating challenge now is to find the others, to map this unseen landscape of the undead, and to listen for their whispers across the vast, silent ocean of space. The universe has shown us one of its secret marvels, a trick we never knew it had, and it leaves us with the most exciting realization of all, that after centuries of watching the heavens, we have in all likelihood only just begun to see what's truly out there waiting in the dark. The greatest mysteries, we can be certain, are still to come.